All right, so I thought we would start off by introducing Newton's second law with a real life example that you can probably relate to. And if you think of everyone's probably been in a moving vehicle before, so we're going to just relate the different aspects of Newton's second law to different types of vehicles and how they accelerate because it has to do with motion. So the first example, we're going to take a sports car for instance. We know that the sports car is going to accelerate quickly. So if you think of a sports car, it can accelerate quickly. It's because of these two things. So we're going to keep focusing on these two factors. So a sports car generally has a small mass. Remember the amount of matter that something takes up in kilograms. But because it's got a fairly strong engine or large engine, it can experience a large net force. So if you think of a large net force trying to accelerate something small, it's going to happen very quickly. Okay, so it's always going to be these three things that we're relating, and if we change one of them, then the third one will always have an effect or change accordingly. So this case, we had a smaller car, larger engine, it can speed up fairly quickly. Now, let's keep the engine at the same. So we have a large net force with a transport truck, right? But its mass has been increased to, let's say, 10 times the amount this sport car has. This transport truck has a much larger mass, even though their engine force might be the same. What happens here? We know that it's going to accelerate slowly. So you're going to see in each of these examples that there's three things that we're looking at: a force, a mass, and an acceleration. And when we change one of those three things, the third one is always affected. So my final example for you is, let's say we have a small car with a small net force or a small engine. So a small net force, small mass, it's also going to accelerate slowly. Okay, so these real life examples are trying to show you how Newton's law and a formula that he came up with always relates these three things, so that if you change one of them, you can calculate how the others are going to be affected. Okay, so let's quickly summarize what the aspects of Newton's second law is. First thing, an object will accelerate in the direction of the net force. This makes sense, right? If we put force, a pushing force on something in the direction to the east, it's going to start moving in that direction. Acceleration is directly proportional to the magnitude of the net force. This big fancy word here, directly proportional, it means that, and let's put a little note underneath here. What it means is that and I'll move it up in a minute, when one is increased, so is the other. And I'll show you how this makes sense. So this is what this one means. And we'll just put this in brackets. Directly proportional, that's what this means. If we increase the acceleration on something, it must also mean that the net force was increased. And vice versa. If we increase the net force on something, it's going to speed up faster. So that's what the word directly proportional means. If we increase one, then the other one's in fact affected as well. Now, if you look at the third point, we've got something a little bit different. And we've got this word inversely proportional. So let's underline that and put a little note about what that means too. It's basically the opposite. When you see this word inverse and proportional, it means they're related to each other, but in the opposite manner. So you can imagine what that means. And let's just copy and paste this one and change what we need to change. When one is increased, if it's the opposite, then what's happening is the other decreases. So think about this. We have an acceleration and we're comparing it with mass. If we increase the mass of something, the acceleration is going to decrease, right? If we put a heavier object on a cart, it's going to slow the acceleration down. So that's what inversely proportional means. When one factor is increased, the other decreases. Directly proportional means that As one increases, so will the other. So that's what those two fancy terms mean. Now let's look at what Newton came up with as a formula to help solve problems involving Newton's second law. So, okay, so his formula states that the net force is equal to the mass of an object times its acceleration. And remember, acceleration is a vector, so is force, so we put the little vector lines on top. And just to distinguish what these are, so mass, M is mass, and that's measured in kilograms. And acceleration is A, and it's measured in meters per second squared. And our net force, all of these things we've dealt with in some way, shape, or form, is our net force, and it's measured in newtons. Now, two things to help you out with some of these calculations. First of all, some of your questions are going to give you your mass in grams. So if you have your mass in grams, you need them to be in kilograms. So if you're given grams, divide by 1,000 to get kilograms, because you want your values always to be in kilograms. That's what Newton's law is based on. If you're given, no, that's good. If you're given kilograms, you want to use kilograms. I think that's the only conversion you're going to have to make. But in order to solve, remember I said that when we have three variables in a formula, we can use a magic triangle. Well, we can use a magic triangle here. Let me make up our triangle, and I'll show you what this one's going to look like. Now, just recall, we're learning quite a few different formulas here. Before we have a unit test, I'm going to make a summary formula sheet that you can actually print out, and you're going to have that beside you when you work through your test. So, magic triangle for Newton's second law. Here's what it looks like. So, force is up here, mass, and acceleration. And remember, all you have to do, and I'm just going to make a little shape here and fill it. All you have to do is, if you're given one of the variable or two of the variables, the one that you're trying to solve for, cover it up. So let's just say we're trying to solve for acceleration, cover it up, and what you're left with is the operation that you complete with the two remaining variables. So remember, if they're separated by a horizontal line, it means divide. If they're separated by a vertical, it means multiply. So if we move that out of the way for now, these horizontal lines here mean that you're going to multiply or divide. Okay, so if you're solving for mass, they give you force and acceleration. They solve for mass. Cover up the mass or the one you're solving for, and it's going to tell you have to take force divided by acceleration. Okay, actually, I'm going to pull this over to our examples that we do on the next page, and we'll work through a couple together. Okay, so here's our first example. A 64-kilogram runner starts walking at 3.0 meters per second east, begins to speed up for 6 seconds, reaching a final velocity of 12 meters per second east. Calculate the net force acting on the runner. So they've given us a lot of information here, but what you want to do first is underline some of the important things and try to identify them as you go. So they've given us mass. Just want to make my pen a little. Okay. They've given us 3 meters per second. This is our velocity. It begins to speed up for 6 seconds. This is time. And our final velocity, here's another velocity they gave us. So now that we have two velocities, we have to establish which one's 1 and which one's 2. So this one's our 1, this is our final, so it's a 2. Calculate the net force. We need to find out what F net is. Okay, so let's look at what we have. Remember, these are the three variables that allow us to calculate net force. So we have mass, we're looking for net force, but we have nothing about acceleration. So what that means is the other numbers that they gave us must allow us to calculate for acceleration. So remember our formula for acceleration. It's our change in velocity divided by time. And you'll have all these formulas in front of you. This is something you can use your notes for. And we're going to substitute these in. So final velocity is 12. Minus our initial velocity, which is 3, over our time, which is 6. And we end up with 8 over 6, and a final acceleration of 1.33 meters per second squared. So what we've just found is just our acceleration. Is that what we're looking for? No. But we needed it to find what we're looking for. We're looking for net force. So if we need to find net force, we need to know our mass and our acceleration. Our mass was given to us. Okay, so here we go. Mass is equal to 64 kilograms. And it's in the units that we want, so we're going to leave that. We just found out what our acceleration was, which was 1.33 meters per second squared. And what we're trying to find is our net force. So let's make our handy dandy cover up tool. Cover it up. We're trying to find net force, so let's cover up the net force. And it will tell us what to do with the remaining. Force equals mass times acceleration. So F net equals mass times acceleration. So we're just directly substituting 64 kilograms times 1.33, and we end up with 85.12 newtons. Now remember, force is a vector, and so we have to figure out what direction that was in. The velocities were in the direction east, so we want to make sure we put that it's 85.12 newtons east. So there's our net force for this calculation. Okay, let's look at another one where we're not using the exact formula. We might have to. Okay, our last example, and then you're going to try a few of these on your own. So example 2, calculate the acceleration. So here's what we're trying to find. Of a baseball that has a mass of 18 grams, so right off the bat, we need to do something with this because it can't be grams, it has to be kilograms, and is given a force of 15 newtons east. So let's write what we have. We're trying to find acceleration, and we were just given mass, but we need to convert that, 18 grams. Remember, to get it into kilograms, we're going to divide by 1,000. So what we end up with is 0.018 kilograms. And the final thing that's given to us is our net force. And it's 15 newtons in the east direction. So we're solving for acceleration. We're going to cover up the one we're solving for, and it's going to tell us what to do with the final variables. So we have to take our force and divide it by our mass. So it's going to look like this. Acceleration is equal to force divided by mass. And that's 15 divided by 0.018. And we end up with an answer of 833.3 meters per second squared, and it's a vector, so we need to put our direction, and it's in the east direction. That's a ridiculously fast baseball, probably not too realistic. Okay, but that's how you're going to solve questions that involve Newton's second law.